John Kutsia, Prof Mark Alexander, David Botha, Tony Marie, as well as Gordon Prestige. I'm sure to most of you Prof Ekama needs no introduction, but here are just some brief highlights of his career. He's had over 35 years in research and teaching in the field of activated sludge. He's published over 150 papers, co-authored 4 of the International Water Association's technical reports on sludge modeling. He's been a visiting lecturer overseas at many universities. He teaches locally and internationally to local authorities, including in Hong Kong and Beijing. He has co-authored online learning material with UNESCO in his field. He's also a fellow of several local and international institutions, such as WISA and the Academy of Science and Engineering. Stefan also reminded me he has been awarded the Order of Makongubwe by the State President for his research in solutions to water-saving problems. This evening he's going to be talking to us on 2 of his most recent research fields, which is separation of urine at source, as well as seawater toilet flushing and their effects on wastewater treatment processes. So Prof Ekama, thanks so much for coming. We look forward to the presentation. Thank you.
I have to start with an apology. This is supposed to be Snape. But okay, it's going to be on every slide, so please forgive me.
He's turning in his grave.
I'm going to be talking a little bit about, I don't know Professor Snape at all. I wasn't born yet when he died. So, and I know I was in a Snape building for many years because I was a graduate from UCT as well, where the building was called Snape. And now we have a new engineering building, and the boardroom of civil engineering is called the Snape Group. So his name lives on within civil engineering and at UCT as well. I'm going to talk about urine separation and seawater toilet flushing. It's a consequence of some research projects, like a smelting together of some research projects that I've been involved in together with the Water Research Commission in some local work, the Hong Kong University of Science and Technology. Hong Kong has been flushing toilets with seawater since 1957. UCT ourselves and the CSIR was also involved in this particular project. So wastewater treatment started 100 years ago mainly to protect human health, and that's changed over the years. So now it's mostly about protecting the environment and human health, and that's basically broadly what I'm going to be talking about. So here is an outline, short introduction, the issues around water, carbon because of our climate change, and energy consumption, of course, has a lot to do with carbon, water quality threats, the eutrophication problem that we've had for many years in South Africa, an emerging problem, micropollutants, especially environmental estrogens, and then pharmaceutical residues. I'm going to be talking about urine separation and how that changes the characteristics of wastewater and simplifies wastewater treatment. What that impact of, if we did manage to do urine separation, how would that impact our current infrastructure of sewage treatment plants? Then should we be doing salination or seawater distribution? I'm going to throw out some ideas about that. Issues around saline sewage treatment, if we were to flush toilets with seawater and the consequences of that. Urine separation and saline water distribution, and then some evaluation and conclusions. This is ongoing work, so we don't have all the answers yet, but there are some ideas here that are finding purchase in Hong Kong, which is setting itself up as a kind of a city of the future in Asia. Alright, so wastewater treatment originated at the end of the 19th century to reduce waterborne diseases. We all know what London was like at around 1860, 1870. Cholera and dysentery were rife, people were dying of typhoid. But over the 100 years or so, we now treat wastewater to protect the environment as well as human health. But a third dimension has been added, and that's this word sustainability. So we want to try and do this wastewater treatment by consuming as few resources as possible, like energy, and emit as little carbon as possible, emit nitrous oxide and these other strong greenhouse gases, as few of those as possible. Urban wastewater treatment, I'm going to, well, sustainability, what does it mean? I'm going to interpret it as meaning that we're improving the effluent quality of the water, the product that the sewage treatment plant is producing. We're going to recover and reuse some of the nutrients, in particular phosphorus, potassium, and magnesium. And we're going to do all this hopefully using less energy, which has to be brought in from outside. And these we will use as indicators of improved sustainability. I have no other way of knowing how to define it. Now, the issues of energy in wastewater treatment is a controversial one, and these two authors from Vienna Institute of Technology, Swarel and Kroes, stated very succinctly. And they say the energy that's available in the wastewater itself, that is the temperature of the water and the organics that we emit or industry emits into the water, is only some 0.02 kilowatts per person. That's 20 watts per person. That's maximum that you can extract. But the power consumption that each of us have, total, connected to the grid, is in the order of 5 to 10 kilowatts per person. And that's not just what your meter reads at your house, that's the factories that make the clothes and everything, food production, it comes to about that. And it's not a difficult number to get to because we know how much Eskom produces, and you just divide it by the population of South Africa and you get the power consumption per person. And that's in the order of that sort of number. So recovering energy from wastewater is never going to solve the energy problem. Okay? That's the bottom line. The water that is produced by the wastewater treatment plant is far more valuable than the energy or the carbon and nitrous oxides that we might produce in the process of recovering that water. So for sustainability, the treated fresh water has far greater value than the energy required to produce it. Like Mark Twain said, and we're beginning to discover in Cape Town, we don't know the value of water until the well runs dry. Okay, our well is running dry. Now, one of the greenhouse gases that are emitted by wastewater treatment plants, not the only one, and that's not the worst one, it's carbon dioxide. And I just want to put it into perspective so that you have an understanding of the quantity of energy that is used in the wastewater treatment by referring it to the amount of carbon that is produced. Okay, so every person that's connected to a sewage treatment plant results in about 20 grams of carbon as carbon dioxide being emitted from the sewage treatment plant. This is 50% of the CO2 that would be produced by the coal burning power station to generate the electricity that is used in the treatment of that water. Okay, so the carbon that comes from the organics to the treatment plant is only half of the carbon that is generated at the power station for the electricity that's consumed at the treatment plant. If I consume 630 kilojoule diet, that's a reasonable diet, then I will emit 6 times, on a 0.12, 6, 7, 8 times more carbon dioxide just by breathing and staying alive than the carbon that is emitted in treating the wastewater that I produce at the sewage treatment plant. Okay, so I produce 6 times more carbon just by being alive. Breathing. Okay. If I drive a small car for 30 kilometers per day, then that 20 grams is only 1% of the CO2 that's produced by my car. And if we begin to go down to how much energy we consume in a domestic situation and how much in the total, then we can see these percentages get very tiny. 0.2% and 0.05%, 1/2000th. So the issue of the energy and the carbon at the wastewater treatment plant is actually not another issue. If we want to look after the planet, there are other places we need to go to address the problem. We don't have to go to the treatment plant. The water is more valuable. Now, I'm not saying that we must just be profligate in consumption of energy at a sewage treatment plant. No, minimize the energy requirements for wastewater treatment plant is good. But the priority is far lower than human and environmental health, which are both closely related to surface water quality and quantity. So human and environmental health requires fresh water quality and quantity conservation. We have to therefore reduce eutrophication and salination. Salination means the acid mine drainage that's discharging into rivers in spent mines or even in operating mines. So what's been happening over the years is that Haber-Bosch in 1934 invented the process that can extract nitrogen and produce ammonia with it. This made ammonia readily available and was spread over the surface of the earth for the last 80 years as fertilizers. These fertilizers grow crops, we eat the crops, the cattle eat the crops, and of course indirectly these nutrients get into the rivers, despite the fact that we have developed biological nitrogen and phosphorus removal systems that can remove these nutrients. But the removal leaves a residue, and that residue we've been spreading out around in the aquatic environment. Also, phosphate is mined, and it is a limited resource. There are predictions that we might run out by 2050, and where we're going to get phosphorus from then, we don't know, but agriculture needs it. So phosphorus recovery becomes an important issue. So technologies have been developed to remove biologically nitrogen and phosphorus. We've played a fairly prominent role in South Africa internationally in achieving that through courageous municipalities and inventive universities. And also sulfate from acid mine drainage is receiving increasing attention. So this is the sort of brown water that you see that decants in low areas from mining areas. Witwatersrand below the city is like Swiss cheese. You can't tell whose mine water is decanting where. It moves from the east and decants in the west because that's the lowest part of the Swiss cheese. And no one can accept responsibility for it because no one knows whose it is. And yeah, it becomes an issue of what I call privatizing the gains and socializing the losses. The miners have been there and they've made their profits, and now your and my taxes have to go in there and pay for getting it fixed up. The banking system is the same. Never get into debt because all you do is work for the banks. Also, privatizing the gains and socializing the losses. It's the same story because these banks are too big to fail. So my taxes gets used to bail them out. Yours as well. Okay, so this is an issue that we're facing here in South Africa. But there is another very important issue that's emerging, and this is the one of the micropollutants. There was a fascinating book that was written in 1998. It's nearly 20 years old. Deborah Cadbury spoke of the feminization of nature, where environmental estrogens and endocrine disruptors, which come from medical residues, are changing the gender of crocodiles, for example. Now, you know, when crocodiles lay a nest, eggs, the temperature of incubation dictates the gender of the crocodile. So if a leguan or something wants eggs for breakfast, that digs out the crocodile eggs and eats the top ones, they're the males. The females stay in the bottom of the egg, where it's in the bottom of the nest where it's colder. They have done work on, and she describes these things on turtles, crocodiles, where they paint these endocrine disruptors that are detectable in the environment in and around the eggs, and they all hatch female. trout hatcheries above and below sewage treatment plants. All the trout that hatch above the discharge of the sewage treatment plant effluent in the river is a mixture of males and females. Downstream are all females. This is a serious issue that we need to address. One of the issues that can address this is this urine separation. And there's quite a lot of research out there which shows that many of these endocrine disruptors and environmental estrogens are emitted via the urine. At least 2/3 of them come out the urine. The other third or so, depending on the type of medication, they come out via the feces. So if we built a urine separation toilet or installed urine separation toilets, it's a toilet, I think many of you would probably have seen them. It's got a little bowl in the front for urine and the feces go into the back. And there's two streams are kept separate. If we did that, then the yellow water, everything that's contained in the yellow water will not be part of what we then would call the brown water. And that makes a significant difference. And the differences are as follows. So with regard to the volume of the water, so this is grey water, and the red is brown water, the feces from flushing, toilet flushing, and yellow is the actual urine volume with a small amount of flushing volume. So you can see that the volume of the water, or urine that you would collect, is very little. It's only 1% of the total water that would be produced, this being the grey and that being the brown. But look what it does to the nitrogen content. The urine, the yellow water, contains 70% of the nitrogen, which would then not get mixed into the larger volume of water. And the brown water only contains 20%, and the grey water 10% of the nitrogen. With the phosphorus, it's 50% is in urine, 40% in the feces stream, and 10% in the grey water, that's shower and bath, kitchen and so on. And micropollutants is about 2/3 in the urine and the other 1/3 in the feces stream. So keeping the urine separate allows you to do focused treatment on the nitrogen, phosphorus, get the nutrients out of the urine, treat the micropollutants in the urine, and then discharge it to sewer afterwards. But I'll discuss all that further in this particular talk. If questions come up as I'm speaking, please ask them, because I think that's quite an interesting engagement we could have. It'll take us a little longer to get to the end, but I do want to provoke some discussion, and so that you don't all just like. Students used to say, listening to me is like trying to drink water from a fire hydrant. It was a compliment for a veiled, say, take it easy, please. All right. So please feel free to ask questions. It may stop the hydrant for a while. So recovery of the nutrients such as magnesium, phosphorus, and nitrogen as struvite, that is a particular mineral that we can make, would help us in mineral recovery, phosphorus recovery in particular. Reduction of the nitrogen and phosphorus on loads on wastewater treatment plants would be a consequence of doing urine separation. And then reduction in the micropollutants, especially these pharmaceutical residues in our over-medicated society. Urine, as I said, contains about 2/3 of these. We would have reduced water consumption, at least, less than about, we'd save about 1/3 of our water, which is our through toilet flushing, 30 to 40 liters per day through toilet flushing, most of which is through urine flushing, because we go to the toilet more frequently for urine than for feces. And then we would have separate urine treatment targeted to the specific composition of urine, as I already mentioned.
Sorry?
Yes?
Just a quick one then.
Yeah.
Are you going to discuss how we're going to separate those two?
Yeah, yes. That's some of the issues that are not completely solved yet, but we can have a discussion on that, yes. I can mention it why we want to do urine separation, not only for the nutrient removal and recovery, but also for, once we start flushing toilets with seawater, we have to preserve the pipes and avoid crown corrosion. And urine separation helps us deal with the crown corrosion problem of having sulfates in the sewers. But that story will unfold as we go. So urine collection is difficult. Yes, it's a problem. It quickly becomes a smelly, odorous fluid. You've probably noticed it. If it's yellow, you let it mellow, and if it mellows a little bit too long, it begins to stink. In our drought, we noticed that. There was such a funny story on Cape Talk Radio the other day. I can't help telling you. So this woman phones up the Cape Talk Radio. I think she was talking to Africa Milani, and he asked the question, what's the protocol if people come to your house and visit? Do you ask them to flush the toilet, or do you say, use the bucket next to the toilet? The lady phones up and she says she found someone that used it, done number 2 in the bucket. The radio station laughed for about half an hour. Anyway, so those are issues that we're facing with urine separation, because urine, to stop us from getting kidney stones, we excrete urea, and that quickly hydrolyzes and becomes ammonia, raises the pH, and then you get precipitation of minerals. And these would clog up pipes if we were to collect the urine in pipes by itself. So perhaps in future we would be embracing our environmental footprint, and together with our solid waste bins, put out canisters with a yellow fluid in it for collection. Who knows how this might go. But whatever we do from the present situation is going to be less comfortable than our current system. But the current comfortable system consumes too much water. And so technically, I think we can do it. We have to change the thinking within our culture and our society on how can we use less water. And the drought is teaching us a lot of things. So the impact of urine separation on wastewater treatment plants, well, it would reduce the nitrogen and phosphorus loads. It would make biological nitrogen and phosphorus removal a lot easier at the sewage treatment plants. In fact, we estimate that it would increase the existing capacity of this infrastructure we have by some 100%. We could treat double the amount of wastewater in these facilities if we didn't have the urine to deal with. Because the urine is about nitrogen removal, and nitrogen removal requires us sustaining the slowest growing bacteria, the nitrifiers, in our sewage treatment plants. And if we don't have to do the nitrification at the sewage treatment plants anymore, suddenly we now have to run a sewage treatment plant to keep the next slowest, and those are the phosphorus removal bacteria. So it will unlock huge capacity in our sewage treatment plants. So yeah, these two photographs here, this is Cape Flats, our largest wastewater treatment plant in Cape Town, 250 odd megaliters per day. Now you're engineers, so I don't have to explain how much a megaliter is. And this is a Hope Koppies wastewater treatment plant in Gauteng. It was the first custom-built wastewater treatment plant. There was a city engineer at the time here was Eric Hall, and based on some scanty experimental work we did at UCT and pilot plant work by the CSIR at Daspoort, they hurriedly retrofitted this plant to introduce biological phosphorus removal, and so that was the first generation of such a plant. I think it was built in 1975. Several water-stressed cities like Cape Town, Port Elizabeth, are considering desalination to augment dwindling freshwater supplies. But desalination is energy intensive and financially expensive. And I'm sure once the dams are full again, and that may happen, but we're not sure, they'll just switch off the desalination plant. And then we have several I don't know how much does a desalination plant cost that delivers 50 megaliters, sorry, yeah, 50 megaliters a day, that's the plan, right? I don't know, a couple of 100 million, right? And then to switch it off is, I think it makes more sense to do something that you can use all the time, because then you're getting value for money. I remember one of my friends in engineering said, any technology that works is cheap. Technology that's not working is very expensive no matter what you pay for it. And I think desalination could be one of those technologies. To distribute desalinated seawater so that upper income people can water their gardens, I think is environmentally indefensible. And we are heading that way. Rather distribute seawater for toilet flushing, save freshwater consumption, and while you're digging up the pavements, replace the broken pipes and save more water, because now we're reducing the leaks. And don't tell me that, oh, it's too much trouble to dig up the pavements. I see open source and digging up the pavements. So we'll do it for fibre, but we won't do it for water. Anyway, Hong Kong has been doing this since 1957. All water in Hong Kong has to be imported from the mainland. And here are some of the costs. Energy consumption for seawater toilet flushing, 13 to 25 watts, because it's it's decided to change by itself. This is fresh water supply. They can do at 50 watts per kiloliter. Reclaimed water at 0.2 to 1 kilowatt per kiloliter, and desalination clearly is the most expensive way of trying to supply water. So Hong Kong has a dual distribution system. They've got a potable water system and a sea water in plastic pipes. 2 pipes go to every house. Plastic pipe brings seawater, you flush the toilet. I've not ever tasted it, but it's there. And potable water to the bath and the kitchen and for all the other water uses. And people in Hong Kong use a water 300 liters per person per day. That's a very high water consumption. But I think it's because it's so hot that they take cold showers all the time. Otherwise, I wouldn't know why the water consumption is so high. This saves 1/3 of the fresh water. Fresh water they can distribute at 5 Hong Kong dollars per kiloliter, whereas seawater that only costs them 1 Hong Kong dollar. This is about 1.5 rands per Hong Kong dollar. So here we're talking about 7.5 rands per kiloliter, and here we're talking about 1.5 Hong Kong rands per kiloliter. But of course, this leads to the problem of sulfates in the sewage. And all cities would have sulfate limits to how much sulfate you can discharge to sewer in the industrial regulations. So of course, municipalities throw their hands up in horror when they say, Ekama, don't be nuts, you'll corrode our pipes in a matter of a year, maybe 2 years. So what happens here is called crown corrosion. So because of the sulfate that's sitting in the liquid fraction of the water, the sulfate reduction bacteria change the sulfate to sulfide gas. That gas escapes into the headspace of the sewer, but there's always a condensate layer up in the top of the sewer. That sulfide gas dissolves into the condensate, and there you get bacteria that do the opposite of what you do in the water. These bacteria will convert the sulfide back into sulfate, and that produces the sulfuric acid that just chews the crown of the sewer, and of course we have sewer collapses. And we want to avoid that because sewers are expensive. Here's one from I believe Virginia in South Africa, the sewer, where acid mine drainage leaked into the sewer, and of course you have the whole process from the sulfate of the acid mine drainage, and they lost 20 to 30 millimeters in the headspace over here, nearly 64 millimeters of pipe thickness over a period of, I don't know, a period of a few years. So it's definitely not a good idea to have sulfates in the seawater. But in Hong Kong, it was for them cheaper to fix the sewers than to buy more fresh water. And as for the biological nitrogen and phosphorus removal that we developed here in South Africa, necessity is the mother of wisdom. It's amazing how that works. And in Hong Kong, they've now developed the SAICE system, as they call it, which allows them to deal with the sulfate in the seawater, and it goes paired with urine separation. And I'm going to elaborate a little bit more on that now. I don't know why it's going. So, what we normally do conceptually in conventional wastewater treatment plants is that we have organic material from feces. These organic materials, the technical term we call it, it's an electron donor. It's compounds that can donate electrons to which is bound energy that the bacteria are really after. And then we connect up the nitrogen removal step. So here is the ammonia that we have in wastewater from urine. We put oxygen into it, and then we produce nitrate through this nitrification step, as it's called. And then we use organic material to change the nitrate into nitrogen gas. And the nitrogen gas escapes into the atmosphere just for the Haber Bosch to pull it out of the atmosphere again and make more fertilizers. But that's the cycle that we're in at the moment. So the organic material, the nitrogen and the carbon and the nitrogen system are locked together. We use both to do the nitrogen removal. The phosphorus removal is a little bit more technical, but I don't want to get into that. What happens in the SAICE system is that here again we have the same as the drawing above, but we interpose the sulfur system in between. And that is shown here. So now we have the organic material, but because we've got sulfate in the seawater, we can transfer the electrons from the organic material, producing carbon dioxide in the process, to sulfate, which is an electron acceptor. So the electrons go from the organic to the sulfate. The sulfate becomes sulfide when it takes up the electrons from the organic material. And then we use the sulfide in the nitrogen removal process, where we again have nitrification in this first step, produce the nitrate, same organisms. But now we use the electrons in the sulfide rather than in the organics to change the nitrate to nitrogen gas. And that's a process on which this SAICE process is based. So this process of converting the organic material is now an anaerobic process, not an aerobic process. That means much less energy, because we're not converting the organics with oxygen as we're doing in the current system. So out the top of this anaerobic reactor, we would have high sulfide and high ammonia, and we go into this packed bed reactor, which is like a media on which specific bacteria grow. In the bottom half, it's no oxygen. In the top half, we have oxygen. And so we retake a recycle from the top, which is now, here the ammonia is converted to nitrate. We take the nitrate-rich liquid and put it into the bottom. So here comes the sulfide and the nitrate, and here we have what is called autotrophic denitrification. And that changes the sulfide back to sulfate and the nitrate to nitrogen gas. And being autotrophic, the production of biomass is about 1/4 of the production of biomass in a heterotrophic denitrification. Which means we are doing two things here. A, we are not consuming oxygen here, and B, we are producing much less sludge, because this is an autotrophic process. And producing much less sludge makes a lot of saving on wastewater treatment as well. Okay, so that's the sustaining process. There's the pilot plant that I was involved in, and I'll describe in a moment how I got involved with their biological sulfate reduction work. This is the USB reactor. That's the anaerobic reactor for converting the organics to sulfide. And these are these two reactors. One was an anoxic and the other one was the aerobic for the autotrophic nitrogen removal steps. So the reason we got involved there was quite fortuitous or accidental. I was on my way to South Korea for a book launch, the book that was published by the IWA, and they wanted the author, the editors of the book, to go there at the book launch because the Korean power company sponsored the writing of this book, and they wanted the editors to go there to sign at the book launch. So we went to do that, and I went on the way past Hong Kong. And when I taught a course to the Hong Kong Drainage Board before, so when the professor at Hong Kong University of Science and Technology, this one here, heard I was coming through, he said, "Oh, won't you give a talk to my postgraduate students?" I said, "Sure, what would you like me to talk about?" I can talk about nitrogen removal, I can talk about biological sulfate reduction, I can talk about mineral precipitation. He said, "Yes, biological sulfate reduction." So I started telling him about the students there and him about the biological sulfate reduction work that we were doing for acid mine drainage treatment. Acid mine drainage treatment is basically chemically based. You add lime, you precipitate gypsum, but you cannot get the concentration of the sulfate down below 2000 milligrams per liter in the precipitation step. And therefore you need some other secondary attached process to change the 2000 down below 250, which is the discharge standard for the sulfate. And that's where biological sulfate reduction begins to play a role. Now, biological sulfate, the cost of biological sulfate reduction is driven by the cost of the organic material you need to drive this removal process. And of course, sewage sludge is free. And at Erwat, there was the Grootvlei mine and the Angkor sewage works 2 kilometers apart. So they pumped the acid mine drainage to the Angkor works. We did the pilot plant work here in Cape Town. Erwat did some of the full-scale work on their reactors, and we basically validated that you could use sewage sludge for a biological sulfate reduction. And so there were a number of things that we found in this particular project, and the one interesting thing is that we found that the hydrolysis rate, which is the rate limiting step of this using sewage sludge, was the same whether we had methanogenic conditions or sulfuric digestion conditions. And of course, methanogenic anaerobic digesters we're very familiar with in the South African context. Research work has been done for many decades on that. Also, we found the same unbiodegradable fractions for aerobic activated sludge and anaerobic digester systems, which was interesting because it means that the aerobic bacteria that we have in our biological activated sludge reactors agree with the anaerobic digestion organisms that what's unbiodegradable for the one is also unbiodegradable for the other. They agree on that. That makes modeling of the systems easier. So the ideas that we then proposed, models that we produced, etc., were applied in this 10 megaliter per day BioSure, as it was called, biological sulfate reduction, and Rhodes University, formerly known as Rhodes University, was instrumental in, together with us, in getting this process implemented together with Erwat at their Angkor sewage works. So they converted 2 of their old Dortmund tanks into these anaerobic digesters and basically validated the concept. Yeah, I think I can step over that, and I probably would best step over that as well, but those are just some of the theoretical ideas that go into these models that we produce. This is the sort of thing that the students are nice doing, but it's got to have some practical value. So unfortunately it has in the end, and but I won't spend too much time on that. So seawater distribution. Coastal cities like Cape Town would then need to install a dual water distribution, potable in steel pipes, seawater in plastic pipes. Now, where dual water distribution systems have been placed, they generally have been low-grade water for flushing toilets and high-grade water for potable uses in the house. But mistakes happen, and plumbers sometimes cross-connect the pipes. And they've had serious problems, and in fact they've had diseases, sicknesses, and in some instances deaths in some of the towns where they tried low-grade reclaimed water distribution. So over the years, the quality of the so-called low-grade water that is dually distributed has been ratcheted up, and it's now almost the same as potable water. For seawater, you don't have that problem. You can take the seawater, you filter it, and then you put a small electrical charge on it. It converts the chloride to chlorine and disinfects it. And every single user is a biosensor. Why? If there's a cross connection, A, it's not going to make you sick because there are no diseases in the water, but it's going to taste awful because someone put the salt cellar over it. So you can phone up the city and say, I think there's a cross connection here because my water just tastes salty. And then the people come and check it out and fix it up. So it doesn't pose any risk for cross connections. So we save water because we're no longer flushing toilets with fresh seawater. It avoids low-grade water distribution and the public health risk of that, and it minimizes the cross connections because through taste conductivity we can also disinfect the seawater quite easily. But it must go hand in hand with urine separation. Why? Because we don't want sulfates in the seawater unless we can put nitrate in the into the sewer first. So the plan is, where pipes can be plastic, it can carry the high sulfate, we call saline sewage, because you won't get corrosion of a plastic pipe. But as soon as you have to move to a concrete pipe, because now the overburden weight on the pipe would crush a plastic pipe, at that point, we need to go to concrete pipes. You have your urine nitrification stations. So these yellow canisters are brought, and there's been studies done at KwaZulu-Natal, at eThekwini. How much do people want to get paid for bringing their urine to a urine treatment facility? And you bring the urine there, and there the urine is nitrified and micropollutants removed, and everything that we need to do to the urine we do there. And at that point, the urine gets discharged into the sewer. Now we have nitrate and sulfate in the sewer, and the bugs will always choose the nitrate first and leave the sulfate alone because they can get more energy using the nitrate than the sulfate as an electron acceptor. So the water, while it's going down to the sewage treatment plant, will get nitrogen removal done to it, and it will preserve the sulfate for the biological sulfate reduction SAICE system that I was planning. So there are some projects now, and sewer modeling is becoming a high visibility project with all the biofilms and all these good things that grow in the sewers to try and work out how much nitrogen removal can we get on the way to the sewage treatment plant. And now we don't have nitrogen to remove there anymore, just phosphorus and organics. And that will make the sewage treatment plant a totally different kind of concept than we have today. A much smaller footprint, both on consumption of power and on occupation of land. That's why I call this talk breaking the convention. Now, the problem is, you cannot change to this kind of treatment system piecemeal. You've got to do it all in one. Okay? And that's where we get stuck, because we find it hard to take the risk and say, okay, let's embrace this and go forward. Alright, so basically this is what I've just said. The nitrate decreases the sulfate reduction, so we don't get crown corrosion in the sewer. The sewer begins to act as our biological denitrification reactor, and it minimizes the crown corrosion. We treat the brown and the grey water in the SAICE process, like the one that I described, and the SAICE process is a nitrification denite packed bed reactor that removes the N and so on. In fact, 80% of Hong Kong's sewage is just treated, just primary treatment on Stonecutters Island, but they are under pressure to reduce the dissolved organic, because chemical precipitation treating of wastewater doesn't remove the dissolved organics and doesn't do anything to the ammonia. So if they couple this idea that I'm talking about here of decentral urine separation, then they can do the nitrogen removal and remove the dissolved organics on the way to the sewage treatment plant, and then chemical precipitation will already give them a very high quality effluent that they can discharge to sea, or even reclaim and redistribute. Right. So, yes?
I'm just trying to figure out, you're saying they could reclaim it, but surely it's softened.
Now you can do your desalination at the end of the pipe, because you've now diluted the water to 1/3 of seawater, which means your concentration gradient across the membrane is much smaller, which means the energy consumption is much smaller, and now it's worth the cost to reclaim the water and put it back into the system. We can let saline water into the sea if we don't want to reclaim it, that's not a problem. But now it becomes worth going to the expense of doing desalination, because now we can put it back into the system. But it won't be as expensive as desalinating at the top end. Alright, so there's a major reduction in oxygen demand at the wastewater treatment plant. Major reduction in sludge production, essentially only the unbiodegradable organics, because the processes that we use are autotrophic and not heterotrophic. So the bugs produce much less sludge. We have major water saving, because we now use seawater toilet flushing, and we've repaired the old broken leaky pipes. However, it only applies to coastal systems only. But then we started thinking, maybe, what about this acid mine drainage? That is a water resource. The difficulty there is the acid mine drainage is not like seawater, in that it has chemicals in it that are potentially dangerous to human health. Those would have to be first removed before you can distribute the partly treated acid mine drainage as a water resource for distribution and toilet flushing. But it's not impossible. And under those circumstances, of course, a wastewater treatment plant doesn't become this bothersome, smelly thing at the end of a pipe. It now becomes an industrial, chemical process where we are recovering resources, and like nitrogen and phosphorus and all those good things. Removing phosphorus by chemical precipitation, and then doing desalination so that we don't increase the salination problem. So we need to re-engineer the whole scheme of the way we're doing it. But the water can be done that way. Maklaleni is one place where acid mine drainage is treated to potable water standard. And the Malakhaleni, what used to be Witbank. And they do that because we're a little bit stuck, because water is owned by the state. So if a person takes the acid mine drain, treats it to put it into the river, that person will want to be compensated for the cost of doing that. And then who's going to pay for it? And that's where is a stumbling block. Here, they treat the water to potable, acid mine drainage to potable water, and then the municipality buys it. So the person, the company that treats the water is getting compensated for it. It's better to do desalination on treated, less saline water than on new seawater. And the Gulf states experience validates that claim. Why? Because in the Gulf states, they take the first pass, desalinate, put it into their distribution system. It goes to sewage treatment plants, they inject it into the ground, and a few kilometers further down they pump it back out again and call it new water and desalinate and do a treat and do whatever they need to do to put it into the system a second pass. They do that rather than take water straight from the sea every time, a one-pass system. They don't have a one-pass system. All right, some conclusions. So, from a sustainability perspective, of course, conservation of surface water quality and quantity is a far greater priority than any energy or carbon reduction that we might achieve in wastewater treatment. That is why I'm saying, I'm saying, tweaking and fiddling around with the existing system is not going to unlock the kind of step change that we need in order to consume less water within our cities. While energy reduction at a wastewater treatment plant is good, it should never be at the expense of the water quality itself. Seawater distribution in a dual distribution system realizes freshwater saving with less energy consumption, carbon production, and nitrous oxide, which has a persistence effect in the atmosphere of 300 times CO2. Methane is 22. Saline sewage treatment combined with source separation of urine can mitigate crown corrosion and obviate nitrogen removal at the sewage treatment plant. Modeling biological sulfate reduction is progressing well, both at UCT and at Hong Kong University of Science and Technology. Applying saline sewage treatment and urine separation, which is dual distribution and collection, requires a major rethink of urban water cycle design and management. It becomes more complex, but we need to embrace complexity if we want to have a smaller footprint in our resource-hungry cities. The co-workers are Dr. Jacques Wilsnach. He was the project leader of the Water Research Commission. He did his PhD at TU Delft and was formerly at the CSIR. He is now at Virtual Consulting. Professor J.H. Chen is the leader of the research group at Hong Kong University of Science and Technology. And Professor Martin Roosdrecht, he's at the Technical University of Delft, where they also do a lot of work on sulfur cycle systems and so on. Thank you for your attention.
Perhaps if Prof Ekama wouldn't mind taking some questions from the floor.
Yeah, please do. I might not be able to answer them, but we can try.
I understand that anaerobic digestion produces methane gas.
Yes.
As an energy source, is that something that could be useful in this world, especially at the end, as you mentioned?
Yes. Yeah. In our current situation, there are treatment plants that have anaerobic digesters. Cape Flats has 3 very large, 6,000 cubic meter digesters. They're like the geyser towers of the south. Yes, they produce methane gas. They have a gas engine there, and they can use it to generate electricity to mitigate the energy cost. But the way we have to run sewage treatment plants in South Africa under what I call the current convention, you never can get to an energy self-sufficient situation at our sewage treatment plant, because we have to run the systems at such long technical terms, sludge ages, to sustain the growth of these slowest growing nitrifying organisms. And that puts one at the consumption of electricity and the recovery of gas. It crosses over, and so we can't generate enough gas to make the plant self-sufficient. That's okay, we can still produce half of the electricity consumption.
Just listening to your descriptions of the parallel and multi-system sewage systems, it reminds me of what's happened over the last century in the development of the motor car internal combustion engine. I'm sure in the 1930s they would have been horrified at the way we build a motor car engine today.
No, I don't understand the connection, but
Well,
maybe you'd like to elaborate.
Complexity.
Oh, complexity, yes. Yes, these days if one of the microchips go, your car stops. and you have to buy a whole motherboard before you get your car going again. Yes, true. Neil.
George, just a couple of things. Thanks very much. Fascinating. When I see a couple of practical problems, one is that, as you already mentioned, it's problematic claiming urine. Second thing is the dual articulation. My own work in stormwater harvesting, the likes of that, shows the dual articulation often ends up so much more expensive than everything else that it's almost not worth it. You're actually probably easier off treating to potable and putting it back into a single system. And then coming to the last comment, which quite fascinates me, is your comment was that it's better to desalinate effluent than it is to desalinate seawater. And that I think is much more useful. And desalinate groundwater is easier still.
Sure, because it's also much lower.
And I mean, I was in Namibia just a couple of months back, and I was fascinated there. I got them to take us through the system from the sewage coming in one end to the glass of water coming out the other end. There's two treatment works actually, separated by 4.5 kilometers. And then they blend that back in to the front there using fresh water on a 2-to-1 dilution.
Yes.
And they've been going like that
Since
for
1972.
49 years. And I start to ask, and an interesting thing about that is that they don't use reverse osmosis. They use ultrafiltration, which of course increases salinity, but because of the blending back, they can bring the salinity back to within limits. And in Cape Town, where our surface water is very low in TDS, we could easily tolerate a system that increases the salinity without any ill effects whatsoever, at a fraction of the cost for seawater desalination. So I think that's where the city's going to go. But it is, but comparing with the Hong Kong model, I think the difference between Hong Kong and Cape Town is that Hong Kong is a very dense city.
Absolutely, that makes a difference. Pipes are short.
And pipes are short.
I agree with you.
And Cape Town is a very low density city with very long pipes.
I agree.
And it will change, but not in our lifetime. So there's a sense in which it's really nice in Hong Kong, but I think we're going to look somewhere else for Cape Town.
Perhaps, yeah, sure. Okay, so these are thoughts that provide a different way of thinking about it. Yeah, in Hong Kong, what they're thinking of doing, in fact, because is to build the urine nitrification reactors on the side of the high-rise buildings. So each toilet has a little pump that injects the urine straight into the reactor. Because they have, a village is like 10, 50-story towers with a shopping mall below, with these towers around the shopping mall and a park. And so that's already a decentralized nitrification system.
So that's exactly what happens here, is that you can get a lot of things, water savings devices, working on a factory, because you have scale.
Yes.
And again, it comes to, it's a density factor again. With our very distributed residential areas, you don't have the density factor.
No, I understand that, and I accept that point completely. Yeah, the numbers may not work out as beneficially in Hong Kong as they would, here as they do in Hong Kong. Totally agree. Yeah.
I don't know the chemistry of this thing, but what if the urine component was discarded at the source? In other words, if you had a septic tank for your urine, and then a French drain, and then the solid wastes, and then you see what it was.
Well, then we pollute the groundwater. The nitrogen. Now, nitrogen is one of the most difficult things to remove. It presents either as ammonia or nitrate, and you can't remove. Well, you can strip ammonia, but that creates all sorts of other problems because you have to raise the pH to do that, and then you start precipitating lime if there's some calcium in the water. So biological processes are favored for removing nitrogen. Once one gets nitrogen into the water distribution, well, into a water source, potential water source, you create all kinds of difficulties of now trying to get that nitrogen out before you can remove that water source. And it's very difficult to remove that nitrogen chemically. You can do it biologically, but that gets tricky. So one wants One wants at all costs almost to not get nitrogen into the potable water that is distributed or in the water sources from which you're going to draw potable water supplies. Nitrogen is a headache.
I would like to ask, how much would it cost to actually install one toilet?
One toilet. Again, it's the economy of scale. If there are thousands of people buying urine separation toilets, they'll get cheap, like cell phones. But if there's one person wanting to import, because you can't buy these separation toilets in South Africa, we had to import the two that we bought, that we used in the project from Switzerland at the cost of some 3,500 rand per pedestal. So yeah, it's expensive. Sure.
It's not difficult collecting the urine if you've got a bucket.
Sure.
You don't need a separate toilet. But if you use that and dilute it and use it in the garden on your plants and the lawn, do you still have a nitrogen problem?
Yeah. You will. All the nitrogen won't be taken up. And you still have so our current sewage treatment plants are not good at removing pharmaceutical residues and environmental issues, these endocrine disrupting compounds. So we've got to do something about that anyway. I don't know what letting the urine settle into the ground, I don't know what that's going to do to those micropollutants. I don't believe we should be letting these micropollutants into the groundwater because it was a wave them goodbye, because I don't know if they may come back while we're not noticing.
I heard that all the trouts in the lake at Toronto are all high on Prozac.
The most relaxed fish on the globe are they? Well, this is where our activated sludge bacteria aren't getting lazy. They're all on holiday there at the sewage treatment plant because of the medication.
We'll get a Prozac.
There's a question over there.
KwaZulu-Natal, I've got a lot of urine
Yes.
toilets now. Has anybody looked to see what is done to groundwater?
No, but that's been collected. Yeah. There was a whole Gates project that studied is it better to pay the people to bring the urine to a treatment facility, or the council goes and does a rounds and collects the water at their cost? And a whole economic study done on it. And then can one produce ammonium nitrate and ammonium nitrate as a saleable fertilizer, as a saleable product essentially.
So those were quite cheap, those toilets, because they weren't really, they were more like VIP special.
Yes. They were UDD toilets.
That's right.
Urine double vault, urine double.
Another question, both west have got the desalination plant, where they now, it wouldn't work unless they actually brought in some of the groundwater to get enough water during the drought conditions. Has any more work been done on
I don't know, I've not been involved with Beaufort West's water works.
So, Peter, have a question then?
Let's go back to that slide with the composition of the yellow, brown, and grey water.
Why does it do this? It takes
There
a photograph
you go.
behind the scenes here. This one, Peter.
Yes. If so much of the potassium, of the phosphates,
of the phosphates,
yes.
In the urine. Half of it's in the urine.
Do we have an overemphasis on removing phosphates from detergents then? Because this whole drive about phosphate-free detergents.
In 1985, the Water Research Commission did quite a far-reaching evaluation on whether South Africa should introduce legislation to stop phosphate builders in detergents. They decided not to influence the market too much, and that the let's call them the soap cookers would impose their own limitations through competition, and that is in fact what's happened, because you'll see more and more of these detergents don't have phosphate in as a builder any longer. So while we've not had legislation, we have seen decreases in the phosphorus content of our municipal wastewaters. they're putting in alternatives like zeolites or calcites. They're a bit reluctant to do it because all alternative detergent builders than phosphate have a higher wear in the washing process. So your clothes don't last as long. You don't wear them out, you wash them out. But the way kids wear their clothes these days, they look washed out before when they buy them on the road.
Perhaps if there are no more questions, yeah, just to close the evening, just to say thanks so much for coming to present to us, Prof Ekama. We really appreciate it. I think it was a great presentation. We do have a small gift for you. It's a black one. You don't often get black ones. It must be special. Thanks so much. Thank you.
Now it's my turn to have a beer.